Thank you, Dom, for the opportunity to speak at this workshop. I'm really excited to be here. It's my first time in Australia. In fact, it's the most negative latitude I've ever been in my life, so quite excited. So today I'm going to talk about topological order from finite depth circuits and measurements. And first of all, let me thank my collaborators. This work was partially done while I was a grad student at Harvard under the supervision of my advisor, Ashwin Vishwanath, and two postdocs, Ryan Thorngren and Ruben Raisin. And this talk is based on a series of works we put out. And through my sheer ambition, I'm going to try to cover a little bit of all of these today. So let me start by talking about dichotomy of quantum states. We can roughly, if we think about quantum states, one way to break them up is you can think of something called short range entanglement and long range entanglement. And the difference is that short range entanglement are states that if you start from a product state, you can reach with a shallow depth quantum circuit. Namely, this quantum circuit doesn't scale with the system size. And long range, of course, requires a circuit that will scale with the system size. Now, of course, this doesn't mean that short range entangled circuits states are not interesting. You can have interesting states such as symmetry protected topological states, or such as the cluster state, which people use for measurement-based quantum computation. On the other hand, we're also interested in long range entangled states, which can exhibit interesting stuff from topological order, critical states, volume law states. These are all states that are hard to prepare if we want to use quantum circuits. Well, today I'm going to be talking about preparation of topological order or topological phases of matter. And why are we interested in this? Well, from a quantum information point of view, we are interested in eventually performing quantum computation or storing quantum states. There are many, of course, candidates, such as using the Toric Code, or even storing quantum information using these exotic fracton codes. But let me put on my condensed matter cap for a bit, and just thinking in terms of realization of these phases of matter. Well, the first one that was identified was the fractional quantum Hall effect in the 70s or 80s. But since then, we haven't really found anything beyond that. For example, even the simplest Toric Code, still, like after 30 years has passed, hasn't really been realized in an actual material. That is until maybe 1.5 years ago. Very recently, we've realized for the first time this Z2 spin liquid or Z2 Toric Code phase of matter. And so there were two groups, one at Harvard and one at Google. And what they did is, what the Harvard team did was they took an array of Rydberg atoms, and under the specific Hamiltonian that governed these Rydberg atoms, if you put them on this lattice, it turns out they form some resonating pattern of valence bond. And this turns out to have some sort of Z2 spin liquid, which is in the same phase as the Toric Code phase. On the other hand, what the Google team did was, using their array of superconducting qubits, they prepared directly the Toric Code ground state using a unitary, and they measured the stabilizers of the Toric Code, and they found these expectation values. So this is very exciting because in a real material, we haven't found a good candidate realizing this, but using sort of the idea of engineered quantum matter, you can actually realize the Toric Code. So this gives a natural question: what other topological phases can these platform hosts, and how scalable are they in preparation? Well, one obvious problem in the term of scalability is because exactly that it's a long-range entangled state. So for example, in the Harvard experiment, what they do is they start with a trivial product state, and in order to tune into this spin liquid phase, what they have to do is they have to tune adiabatically. And since you're changing from a trivial state to a non-trivial spin liquid state, you need to go through a phase transition. And in terms of the time you need, it'll scale with the system size, because if you need to evolve adiabatically, as the gap closes, you need to go slower and slower. And as the system size approaches infinity, this will take longer and longer. At the same time, what the Google team did was they used a linear depth quantum circuit. So it worked well for their specific size of platform. But if later they get a larger chip, right, it's going to take a deeper depth to prepare. So this is very specific to this size of the chip. So it seems that, well, all such preparations are slow and not scalable, right? As I told you, it's a linear depth circuit. But what this is, you can even, there has even been work that bounds the depth of the circuit, that if you only use unitary evolution, you indeed need linear depth circuits. But now what condensed matter people usually don't think about is actually measurements. And yes, not scalable. Oh, if you want to prepare a larger Toric code, then it'll take longer to prepare, because the depth of the circuit will scale according to the system size you want to prepare. You can do what, sir?
You don't mean scalable in some technical sense, right? You just mean it takes longer.
Oh, yes. In this, yeah. It just means it takes longer. Yes. Not that they can't make that chip. Yeah. But now, one thing you don't do you don't usually do in a condensed matter system is perform measurements. But it turns out that that's what you think about all the time when you do error correction. And in fact, there's a fast way to prepare the Toric code by measuring a short range entangled state. So let me just go through that real quick. I'm sure people here are familiar. You start with a product state, and you prepare a 2D cluster state, and that can be performed by a shallow depth circuit that's just a bunch of control Z's. And these are the stabilizers of the cluster state on this particular graph. And now what I do is I measure all the red sites in the X basis, and note that this is non-unitary, so it's something very violent. But what happens is the output state is some excited state of the Toric code. Depending on the measurement outcomes, you're going to get this classical value plus or minus 1, and it's just going to say whether this vertex term is plus or minus 1. You can still deterministically prepare the ground state if you know these measurement outcomes, because knowing what these values are, suppose I find a minus here and a minus here, what you just need to do is you found two errors, like two E anyons. And so you just need to apply some string to correct this error. And so you know exactly where they are because you measured them. And from that, you prepared a Toric code ground state. So to summarize, using finite depth circuits and measurements, we are able to circumvent this linear depth bound, and you can prepare long-range entangled states in a finite depth circuit. This, of course, is not new. It's been known since people have been thinking about cluster states. But it raises an interesting question. So here, you can also generalize to arbitrary stabilizer states. Basically, what you do is, well, if you want to prepare your state, you just measure those stabilizers. And depending on the measurement outcome, you just correct. Now, the question is, can we prepare any other interesting states? Yes. Yes. That's correct. So the classical processing will still be linear depth, but what we're using to our advantage here is that we've changed the light cone from the usual Lee-Robinson and the quantum one to a classical one, so we can still communicate sort of with the speed of light. So we change our speed of light, and effectively in the lab, the speed of light is infinity. So that's how we cheat, basically. Yeah. So so for an arbitrary stabilizer state, you can just measure the stabilizers and fix them. So it gives you a way to prepare an arbitrary stabilizer code. So it begs, oh, sorry. Let me just mention that to prepare such a state, the Toric code in this way, in recent experiments, has only been done as in like last week, where you can actually prepare the Toric code state by measuring the stabilizers. And the fact that you can prepare the ground state of the Toric code requires this feed forward, where depending on the measurement outcomes, you need to correct. And that is not yet available in every platform, but it turns out recently, and this is some work in collaboration with Quantinuum, what we showed is you can prepare the ground state of the Toric code using a measurement-based preparation. So even if you go to larger system size, that would still scale with a finite depth circuit by using measurements. And we found very high values for the expectation value of the Toric code. And you can even do something similar to introduce defects in the Toric code where you can exhibit some EM duality. So I'm just flashing this slide to show what current platforms are capable of. It's a little out of chronologically order, but let me just return to the question at hand, which is knowing that you can prepare long-range entangled states by measuring short-range entangled states. Namely, there's a finite depth circuit plus measurement protocol to prepare long-range entangled states. So what other topological phase can or cannot be prepared in this way? And second, what platforms are natural to realize this? So what I'm going to be talking about today is that how to go beyond measuring cluster states or measuring stabilizers to prepare stabilizer codes. What we find is using these methods, you can even prepare non-stabilizer codes, such as quantum doubles, these type quantum doubles for certain groups. And basically, the ingredient that allowed us to do all this is related to the fact, which I'm going to explain, that what this protocol of measuring the cluster state is secretly doing is gauging. So this is exciting because once we know how to gauge something, we can prepare a gauge theory of it. And, oh, sorry, I'm really bad at this control. You can prepare long-range entangled states by knowing what symmetries you can gauge. And the output of all this results is basically, you can think of it as a cookbook. For example, you give me your favorite state you want me to prepare. I can give you a recipe by initializing with certain states, applying some gates, and measure, fixing depending on the outcome, and you can prepare your favorite phase of matter. And I'll be talking about what we think you can or cannot prepare using such methods. So the outline of my talk is the following. I'm going to talk about how measuring cluster states secretly is implementing the Kramers-Wannier duality, or the so-called gauging map. And I'm going to also talk about what states can or cannot be prepared using finite depth circuits and measurements. I'm going to mention two potential ways to realize these interesting states. One is with Rydberg atom arrays, and the second is using Google's quantum chip to prepare a potentially interesting non-Abelian state. So let me just start with this. I'm pretty sure people here are familiar with the cluster state, but let me just overview it real quickly. So starting with the product state, you can prepare a cluster state by applying this unitary control Z, and these are the stabilizers of the cluster state. I just want to offer some intuition on why, for example, in 2D, you can measure the cluster state and prepare the Toric code. The analogy in 1D is measuring a 1D cluster state on the odd sites give you a GHZ state. So let me just go through that real quick. So I'm starting with the product state, and I'm thinking of these stabilizers, X, and you can think of them as all the spins pointing to the right. I'm gonna put an alternating lattice where I have blue spins and red spins. I'm gonna keep the red spins pointing to the right, but I'm gonna write the blue spins as a superposition of up and down. So this sum here is now a superposition of all blue spins being in an arbitrary up-down configuration. And I'm gonna denote that when transiting from the up spin to the down spins, you have this so-called domain wall, which I'm drawing over here. And note that this domain wall is passing through a red spin. Now, what is the cluster state entangler control Z doing? Well, control Z, what it does is, if the blue spin is up, I act with identity on the red spin, and if the blue spin is down, I act with Z. So now notice that Z what Z does is it basically flips a plus state to a minus state. And you can see that if you're on a domain wall, you're going to apply Z once. For example, from the upspin here, nothing gets act, but from the downspin here, plus gets flipped to minus. If I'm off the domain wall over here, then nothing gets act. And if I'm off the domain wall on this side, you apply Z twice, so you also don't do anything. So basically, the interpretation of the cluster safe wave function is that you're thinking of a wave function where the red charges are bound to blue domain walls. And in fact, this property, it characterizes this cluster state as an interesting symmetry protected topological state. Now, why is this picture important? Well, now next, I'm going to just measure the red sites. You probably all know how it works in the stabilizer formalism. Once you measure the red sites, what happens is you're going to get an outcome, which is little x, which is plus minus 1. And if I measure in the x basis, note that this ZXZ stabilizer doesn't commute with the measurement, the second one. But you can take a product of that, and that commutes with the measurement. So you also know that this product x is equal to 1. And now this is almost a GHZ stabilizer up to the fact that you need to fix these measurement outcomes. Now, why is that doing that in this picture of charge decorated on domain walls? Well, what I'm doing basically by measuring x is I'm measuring the value of the charge. So I'm measuring where the charges are on the red sites. And basically what that does is, since the charges are bound to domain walls, what I'm doing is I'm collapsing the superposition where charges are bound to domain walls to one slice of it. And so suppose I find my measurement outcomes to be plus minus minus on the plus minus plus on the red spins here. What it's doing is it's just collapsing all the possible domain wall configurations to that satisfies the one where the domain wall is attached to the charge here. So there are two configurations which has this domain wall, which is the one where the spin is up and turns down here, and the one that's down and it turns up here. So by measuring the charges, I'm collapsing this domain wall to a very particular configuration. And now basically this is almost GHZ because we know where the domain walls are. We just need to fix it. So in order to make it a GHZ state, we just need to flip all the domain walls. We just need to remove all the domain walls by flipping all the spins that were down over here to be up. So by acting with X in that region, that's just going to be your GHZ state if I remove the red sites. So that's why measuring cluster states is giving a GHZ state. Now, what I'm going to talk about next is how you usually think about it from the stabilizer formalism. What I like to offer is a different way to think about it in terms of thinking of a cluster state as related to the Kramers-Wannier duality. So maybe the easiest way to think of it is to think of the cluster state as some sort of tensor network. So I have some matrix product state which has stabilizers, which is ZXZ as shown. And note a little fun fact that if I just flip all the blue legs upwards, then instead of a state, now you get an operator which inputs the red sites and outputs the blue sites. And what that does is if you input an X operator down here, it's going to spit out two ZZ operators up top. And that's basically the Kramers-Wannier duality. So using this insight, what we've done is if you somehow use the cluster state and you input a paramagnet, which is the X stabilizer, you output a ferromagnet, which is the ZZ state. So using the Kramers-Wannier on the product state, that's why you get the GHZ state. And similarly in 2D, if you use a 2D Kramers-Wannier, which is shown in this tensor network. Sorry, I'm messing up the buttons. If you use this 2D cluster state and flip the blue legs up, it's going to turn X into a product of ZZZZ, and that's the Toric Code stabilizer. Moreover, you can generalize this to any CSS code. In fact, if you just need to choose this graph to be the tanagraph of that corresponding CSS code, and by acting that operator on the product state, you're going to prepare your CSS code. So now, how do we turn this into a measurement? Well, the basic idea was what I already showed. What I did was we prepared all the red and blue sides in the plus state, applied this cluster state entangler, and measured the red sides. For now, let me just put it as a projection to make it life easier. The claim is I can actually remove the red sides and have this be an arbitrary wave function. And the claim is that this acts as Kramers-Wannier. To see that, let me start with an X operator, and let me push it through the cluster state entangler, which is Control Z. You're just going to get ZXZ. And now when I act with this plus state as a projector, X is going to get absorbed. The eigenvalue is +1, so I get ZZ. So the fact is that you can perform this operation. Whatever your wave function is on the red sides, just couple it to some ancillas within the plus state, apply Control Z, and project to the plus state, and that implements Kramers-Wannier duality. So that's the relation between the cluster state entangler and Kramers-Wannier. I guess I should also note that this picture is symmetric, so you can also convince yourself that putting X up here will also result in ZZ down here. So it is exactly the Kramers-Wannier duality. So using this insight, what I've just showed is that the Kramers-Wannier duality, or the gauging map, you can actually implement it on any input state. It doesn't need to be a product state. So the fact that measuring the 1D cluster state gives you the GHZ now generalizes to, if I apply this 1D Kramers-Wannier on anything in the paramagnetic phase, I don't need to be in the fixed point of the paramagnetic phase, which is the plus state. I will end up somewhere in the ferromagnetic phase. So for example, if I want to get some long-range entangled state, I don't need to actually start with the product state. I can start anywhere in the paramagnetic phase. I do this procedure, the output is going to have some long-range order of a ferromagnet. Similarly, in 2D, I use the 2D cluster state to prepare the Toric code. This now generalizes to the fact that if you prepare a paramagnetic phase, it can be anywhere in this phase. What you obtain is something that is in the deconfined phase of a Z2 gauge theory, in which the fixed point is the Toric code. But again, you don't need to be at the fixed point. You can be anywhere in the paramagnetic phase. By gauging this gives you a deconfined gauge theory. So let me just make a quick comment for people who think about gauge theory. There's a very interesting connection between the Toric code and the cluster state, in the sense that you can actually think of the cluster state as like a Higgs phase of the Toric code. One way to see it is, suppose I start from the Toric code. What I can do is, how do I go back to the 2D cluster state? Well, if I just measure ZXZ on every bond, I'm going to exactly go back to this 2D cluster state. But what is this ZXZ doing? Well, the X operator is creating a pair of anions, and the Z is hopping sort of physical. You can think of it as the vertex being a matter field and the edge being a gauge field. So what this ZXZ is that it's hopping sort of E anions, which are connected by a gauge field, and this gauge field is given by X. And by proliferating this, you're performing sort of like a Higgs condensation to obtain a short-range entangled phase. And we know that the Higgs phase is short-range entangled because there's no anions in there, because you already proliferated them. But now it shows us why measuring the cluster state gives us back the Toric code. In some sense, the measurement on the vertices of this cluster state is performing some unhiggsing, because the Higgs condensate corresponds to a superposition of all these E anions attached to strings. And by measuring where the E anions are, out of the superposition, you're just going to select out a slice of it. And this slice is exactly a slice of the Toric code, which you started with. So then this gives an idea why measuring the cluster state, which is short-range entangled, gives you long-range. It's a superposition of anions hopping all around over the place. Okay. Let me just stop and ask if there are any questions up till this point. I forgot to mention, if there are any questions, please feel free to let me know.
So everything you presented so far is based on that particular choice of the two cluster states.
Yes, yes.
So if you change your 2D cluster state, do these results change significantly, or?
One thing for the, well, so one thing you have to assume is that the cluster state is bipartite and you measure one sublattice. But in general, it holds more generally for any bipartite cluster state. You're basically, if you think of that as a tanagraph, you're going to measure some CSS code. You're going to prepare some CSS code. And similarly, you can think of that as gauging some symmetry, whatever that symmetry is. It could be fractal symmetry of Haas code or something if you want, for example. Yeah.
So that 2D cluster state has some kind of symmetry protected order still, like
Yes.
the symmetry is weird, but there's some kind of symmetry protected order. If you were thinking about that Z2 gauge model, there's this whole thing that there's that sort of deconfined kind of non-trivial phase, and the X phase, and then for Z2 it's actually connected to a trivial phase, so all the states are uncoupled. There's actually no phase transition over there. You know, like, yeah, so there's,
Yes.
Some often people say in the literature, oh, that Higgs
Yes,
phase,
the Higgs phase and the confined phase are connected, and it's exactly this cluster state entangler.
is that maybe, so I suppose what I'm saying is if the Higgs phase is really got some symmetry predicted topological order, is it possible that the story is a bit more complicated than that, or is that cluster state for these purposes?
So there is some work by Ruben Vereisen, which exactly study what you asked, and it turns out there's something subtle, because it turns out for this particular cluster state, it's in the 1D cluster state, it's protected by 2Z2 symmetry for each sublattice. In this case, it turns out to be protected by a Z2 symmetry on each red, but a one form symmetry, a closed loop on each blue. And now there's some subtlety of whether the one form is emergent, and it turns out you get a boundary transition. So in fact, what they observe is if you define this model with a boundary, you actually see a boundary transition related to this one form symmetry. Yeah, so there's something subtle going on there. Yeah, that's very interesting. Yeah.
Sorry, can you define the Higgs phase in the confined phase?
So the deconfined phase, you can think of it as, well, as sort of like a spontaneous symmetry breaking of this higher form symmetry. And the QI version of that is saying, well, you have logical operators, and that's because, and that's basically breaking some degeneracy, right? In the GHZ state, you're spontaneously breaking some Z2 symmetry. And that's why you have a degeneracy. In the Toric code, you also have some degeneracy. That's your logical state. And that's coming from breaking of a higher form symmetry. The 2D cluster, sorry, you were asking what defined the Higgs phase? Yeah, so the Higgs phase, well, it's going to be a little circular, but you define it as some condensate of condensing the charges. You allow the charges to hop everywhere around. So you no longer sort of have your information protected. And that's why you don't have a degeneracy, which is the cluster state. It has a unique ground state. But maybe not sure if that was helpful or not, but. Okay. So let me just mention the first application, which is you can prepare many of these states, turns out, with Rydberg atom arrays. And this morning, we already got a very good introduction about Rydberg atom arrays. I'm just going to pretend to be a theorist and say, well, you can think of Rydberg atom arrays as modeling a qubit where you have a ground state and a Rydberg state, which is some highly excited principal quantum number. And you can think of it as a two-level system. And basically, the effective Hamiltonian of such a Rydberg system, you can think of it as an Ising model, where you have some transverse field coming, some longitudinal field, and you also have some interaction between two Rydberg atoms, where this interaction, you can think of it as some 1 over r to the 6th potential. The nice thing about this is that in the limit where so-called the blockade limit, you can think of this potential as sort of like a hardcore constraint, and it more or less models very closely a nearest neighbor interaction. So because the next nearest neighbor is so small, you can sort of approximate it as a good nearest neighbor. And now what you can do is, it turns out the cluster state entangler up to some single site gates is more or less the evolution of an Ising term for a specific time. So what you can do is, by evolving with this Ising term, so you can start for Rydberg states in the plus state and let it evolve with the innate Ising Hamiltonian that governs the system, and then measuring half of the sites, that'll prepare your long range entangled state. So for example, you can prepare a GHZ state this way, and you might ask, okay, how does this 1 over r to the 6 potential in practice affect the fidelity of preparing, for example, compared to an ideal cluster state? And it turns out that it's pretty good, and you can even have the timing of this Ising you can even evolve for the time can even be off by a bit, and the correlation length of your GHZ state can be pretty large. For example, if you miss by 10 to the minus 3, your correlation length turns out we calculated is 500,000 sites. So you can, in principle, prepare a 5-meter cat if you want in the lab, if we ever get to 500,000 qubits. And it turns out this is the 1 over r to the 6 potential gives very high fidelities. For the Toric code, one can also prepare it similarly. And it turns out that for geometric reasons, we want to maximize the distance between the next nearest neighbor between red and blue. And it turns out that the honeycomb lattice works better than the square lattice. And using this, you can calculate what the fidelity, the expectation values are, and they're pretty high. And one day, if we get 3D Rydbergs, one might even be able to prepare these exotic fracton orders where you have restricted mobility. In this particular model with the stabilizer, it turns out that the excitations can move in the z direction freely, but in the xy plane, they cannot move. And if you want to move them, you have to apply this sort of fractal operator. And it turns out using this, putting Rydbergs in this configuration, you can get quite good results. So that's one application. So let me now move on to the second part of the talk. And now I'm going to address a more theoretic question of what non-Abelian states can we or can we not prepare. So it turns out that you can generalize the cluster state pretty easily to Abelian groups. In fact, you can even generalize it to finite groups. And there's this very nice paper by Brell, which generalized the cluster states to non-Abelian groups. And it turns out that if you put it on this bipartite lattice in 2D I showed, if you project to the plus state on this cluster state, it'll prepare you the quantum double model. Now, this I'm sort of suggesting that you can prepare all these non-Abelian theories by simply preparing this cluster state and then measure. The subtlety is that when there's a subtlety when I turn a projection into a measurement. So recall that in the Toric code case, when I perform a measurement, it's informing me whether I have an E anion there or not. And if I get +1, it's good. I don't have an E anion, I'm good. But if I get a -1, I need to fix that outcome. And based on these measurement outcomes, I need to pair up these E anions to prepare the clean ground state of the Toric code. It turns out in the quantum double model, what you measure on the vertices turns out to correspond to non-Abelian anions. And non-Abelian anions are sort of a problem because the 2 points sort of have some non-trivial entanglement, which implies that if you want to apply some string operator to pair them up, it cannot be applied in finite depth. It turns out that for these non-Abelian anions, you can show rigorously that you need a linear depth circuit in order to move such anions. So this is an obstruction. You can't pair up non-Abelian anions, so it doesn't give you a protocol to prepare non-Abelian states in finite time. So what we figured out is for certain non-Abelian states, you can overcome this. And what we do is, even though you have a non-Abelian symmetry that you effectively want to gauge using this Kramers-Wannier duality, you can break it up into easier problems where you're always gauging something Abelian. And once you gauge something abelian, you can always pair up abelian anyons along the way. And those are easy to do. And let me demonstrate how we do that. So let me start by talking about the simplest non-abelian group, S3. You can think of that group as the symmetry of the triangle. So there's a Z3, which you can think of as rotation of the triangle, and a Z2, which acts as reflection. And this is non-abelian because if you reflect before you rotate, you're going to rotate in the other direction. So these two operations don't commute, and that's given by the sort of semi-direct product symbol here. Now, the way you can prepare this non-abelian topological order, well, first of all, let me say a naive but wrong way to prepare it. If I start with a qubit and a q-trit, I can apply this Kramers-Wannier duality by applying by preparing a cluster state respectively for each and then measuring. But that turns out will not prepare S3 because that'll just prepare a Toric code of the group Z3 times Z2 or Z6. That's not going to give me my non-abelian state. What I want to do is I want this Z2 to act correctly on the Z3, because currently the Z2 and Z3 layers, they don't talk to each other. What I want to do is, it turns out you have to add an extra layer of unitary. So first of all, I'm going to use a Z3 Kramers-Wannier duality to prepare the Z3 Toric code. How does that work? Well, you just prepare a cluster state for the Z3 layer and measure. After feed forward, you're going to get the Z3 Toric code. And basically, the only ingredient you need to add, turns out, is a unitary, which you can think of as like a controlled charge conjugation operator. The charge conjugation on q-trits is defined as such. It's swapping it's keeping the 0 state invariant and swapping 1 and 2. But that's exactly the action of the Z2 acting on the Z3. The reflection is leaving the identity invariant, but it's swapping the left rotation and the right rotation. So basically, it turns out that if you act this unitary on your Z3 Toric code, and now you go ahead and prepare a cluster state and measure, you're going to get the right symmetry action, and you are able to prepare this S3 quantum double model. So, so the important part is this unitary, which gives you the right action of your non-abelian symmetry, it turns out. So this naturally generalizes to other non-abelian states. As a stepping stone, you can similarly prepare what are these so-called metabelian groups. And these are two groups. You can think of it as a group extension of one abelian group by another group. And basically, the formula is very similar. You gauge the n, the normal subgroup, to prepare a Toric code with an abelian group n. You apply some unitary such that the symmetry acts correctly. And then you gauge the quotient subgroup, and that effectively is equal to gauging the whole G group. And for those who think about in a condensed matter way, this U operator turns out to be an entangler for a symmetry enriched phase. In particular, if your group extension is a split extension, like the case of S3, what the quotient group does, it permutes anyons. And in the case of a central extension, this quotient group will fractalize on anyons. So to generalize this, it turns out that what this generalizes to stuff, the so-called solvable groups. And what a solvable group is a group where you can obtain it by a finite number of group extensions by an abelian group. So the way we prepare it, turns out, is let us start with a symmetry group G. It turns out a group is solvable if you compute the commutator subgroup of that and the commutator of that, and eventually you arrive at the trivial group. That's one way to define a solvable group. And basically, to gauge this symmetry G, what we do is we apply some Kramers-Wannier duality to work our way back up. Namely, we first gauge the symmetry N1. We apply some unitary such that after we gauge the difference or the quotient, we end up gauging N2, and we sort of work our way back up until we gauge the whole group G. So in the case that this is abelian, well, that's the case where you compute the commutator and you eventually you automatically get the identity. And these metabelian groups are the ones where you have to do the commutators twice. So basically, given a group G, there's some number of rounds of unitaries and measurements you have to apply in order to gauge that group. And it turns out for quantum double models, it's related to the so-called derived length of the group, the number of times you have to do commutators. So by now, at this point, you might be thinking, whoa, measurement is so powerful. You can probably prepare any state in the world or in the universe now. Let me now talk about some no-go, which is, it turns out there are some states that are too hard to be prepared by measurement, finite depth unitaries and measurement. And this turns out to be related to some esoteric math related to Galois. So you might have heard an interesting fact that when you learn algebra, that if you have a quintic polynomial, you cannot write it. You cannot write such a solution in terms of radicals. So there's a quadratic formula, there's a cubic formula, but there's no formula for the quintic. It turns out that this fact has some deep relation, we think, to preparing these quantum double models. And basically what Galois tells us is that basketball is easy, volleyball is easy, but soccer is hard. So to translate my joke just now, the symmetry group of the basketball, if you have a quantum double model of that, or it's easy enough to prepare with finite depth circuits and measurements, and same for the volleyball. But the symmetry group of the soccer corresponds actually to this symmetric group of 5 elements. And this number 5, turns out this symmetry of the soccer is too hard to be obtained by group extensions. And so if you happen to have a quantum double model corresponding to the symmetry of the soccer ball, then my claim is that you cannot prepare it with finite depth circuits and measurements. So that seems to be quite shocking, because for these quantum double models, we know that there are sort of tensor network representations of such states. You might naively think, well, there should be a way to just perform finite depth circuits and perform measurements. That should give you a good tensor network state. But somehow, because of this argument, we sort of have a physicist proof that you cannot prepare this. So I won't go into the details of why. I sort of present a vague explanation of using group extensions why you cannot prepare such groups. But yeah, so if you're interested, please feel free to ask me afterwards. Let me stop again and ask if there are any questions up until now. If not, I'm going to talk about the last part, which is preparing a non-Abelian state from a single round of measurement. So I've just shown that for all these so-called solvable groups, you can prepare them with finite depth circuits and measurements. And let me impose a more strict question and ask, how many rounds of measurement or shots do I need to prepare a state? So for example, in the Toric Code, you only need 1 round of measurement. And for the S3 group, I show that you need 2 rounds of measurements. You can ask, like, can we lower this? And in particular, you might ask, well, why do we care about this question? Well, the first one is that in current platforms, this mid-circuit measurement is still in development. It's not very easy to perform many rounds of measurement and feed forward. So we might want to minimize the number of rounds. And the second is it further, as a theoretical question, it grades these topological phases. Instead of everything is hard, it tells us how many rounds we need. And that gives you a hierarchy of how hard these states are prepared. So let me just ask an extreme question, an extreme case. What if I'm only around 1 round of measurement? So, well, what if you only got 1 shot? So can you prepare anything interesting beyond stabilizer states, or those that have abelian topological order? And the answer turns out to be yes. It turns out that if you go to the symmetry of the square inset, which is this group D4, it turns out that instead of using 2 rounds of measurement, you can prepare it in only 1 round. And let me just explain the intuition. So the naive way, which I explained earlier, what you would do is you can think of this group as two reflections, which is interchanged by a third reflection. So what I would do is first I would prepare a quantum double of this normal subgroup, which is just basically two stacks of Toric codes, Z2 Toric codes. And what I do next is I gauge the symmetry that swaps these two layers. So if I measure this, so if I prepare these Toric codes and it turns out I don't pair up the anions before, what's going to happen is once I gauge this swap symmetry, the E1 anion is going to turn into E2, it's going to permute into E2. And once that symmetry is gauged, it's going to transform it to each other and it's going to form something like a doublet. And that doublet is exactly a non-Abelian anion. So if you don't fix it before, once you gauge this swap symmetry, you're doomed because now you have to pair it up with the linear depth circuit. So what you have to do is, well, you have to clean it up first and then measure a second round. So you can't put these two measurement rounds at the same time. That will not work. However, instead of measuring E1 and E2, if you instead measure the combination E1, E2, and M1, N2, one can convince oneself that this also prepares the same Toric code state. You just measure the stabilizers corresponding to these anions. And now if you measure the swap, well, the difference here is that E1, E2 is a singlet. It does not transform into something else. So even after you measure the swap, it's going to remain an abelian anion. And then you can measure all of these at once. So that gives you a way to prepare this D4 topological order. We found a nice way, actually, to implement this with only two body gates in. So here is the recipe. And let me just break it down how it works. You start with the product state, and you prepare some control Z connecting. So the lattice is the vertices, edges, and plaquettes of the honeycomb lattice. If you prepare the control Z and between vertices and plaquettes, and if you measure the plaquettes early, that actually prepares color code, which is two copies of the Toric code. And then you perform some single side rotation, which turns the swap symmetry into a prod X symmetry. And basically what you do next is you gauge that symmetry. You apply control Z from vertices to edges, and then you measure. So using this connectivity, you only need two body gates, which is control Z, and the only non-Clifford gate that appears is this sort of T or T dagger gate here. So one can even implement this on the Google chip. We figured out a way how to embed this in the square lattice, and it turns out you only need a depth 11 circuit. So if they have larger chips in the future, you will still only need a depth 11 circuit. And this, we think, is the easiest example of non-Abelian topological order that can be prepared in a quantum device. I guess I'm low on time, so let me skip this point about what other phases you can prepare in one shot. Let me just summarize now that what I've just shown you is a new way to think about phases of matter. We can define two phases of matter under measurements to be equivalent if you can prepare one from the other using finite depth circuits and measurement. And instead of all of these being in different classes, it collapsed the classes into a Corsair equivalence class, where all of these solvable groups are preparable. And we think that certain non-Abelian groups and certain anion theories like Fibonacci, we think you cannot prepare. And furthermore, you can further ask how many rounds it takes you to prepare. And like the Toric code, which we use 1 round, surprisingly, D4 only uses 1 round. S3, we still think uses 2 rounds. We think you cannot improve that. So that gives you a hierarchy of quantum states, which you can classify. So let me just stop here, and I'll flash some other fun facts, which people can ask during the question.
Great, thanks, Nat. Any questions? So Andrew's hand moving. Oh, yeah, start with Andrew. No? Yeah, okay, we'll get for Gavin then.
Yeah, I was just wondering, like, to take a little far out, could you maybe prepare like one double of a continuous?
We did think about that, but the analogy of the cluster state turns out to be a chiral state in that case, and we don't know how to prepare that using an exact quantum circuit. So even though there might exist a unitary that prepares that, you might need to have some tails in your circuit. Namely, it might have to be an evolution of a Hamiltonian that has like decaying correlations. So that might make it a bit harder. And also so in terms of quantum devices, there are many obstructions to that. Also, because for a continuous group, you might need an infinite Hilbert space. So yeah, there are many obstructions to do that, but definitely there are some connections to be thought about that. And you can think of it as related to particle vortex duality, it turns out. So Kramers-Wannier duality in the finite case turns out to be particle vortex duality in the continuous case.
So I suppose I have two quick questions. So the first one is Kramers-Wannier has like a three-dimensional version as well, right?
Yes, yes.
Some kind of strongly coupling duality.
Mhm.
I'm wondering if this kind of approach or line of thought gives any insight into 3D models. And I suppose my other question was, if you've got certain non-Abelian neon phases where you can't prepare in constant time even with measurement, do you have some intuition about whether that says something about thermalization or some kind of like, would you expect there to be any physical process like something to a bath or whatever that would prepare approximations to those states?
Right. Okay. So for the first question, in 3D, it turns out to prepare the 3D Toric code, there turns out to be two Kramers-Wannier dualities, and one corresponds to measure the vertex term and one corresponds to measure the plaquette. And that turns out to be related to gauging a zero form symmetry or gauging a one form symmetry. So there are two ways you can arrive at the same state, turns out, whether you measure vertices or plaquettes. And the second is, so all these states, well, since it's a 2D state, it's not gonna be stable to thermalization. But a related thought is what is the circuit depth with measurements to prepare such non-solvable states, and so Tim Xia and company has a recent paper where they showed you can prepare it in log L depth. And what they did is they used the fact that the state has a Mera representation, the string nut model has a Mera representation, and they usually use measurements to teleport qubits around. So the log L just comes from the log L depth of your Mera. One fun thing I can mention though is that it turns out for preparing these non-solvable states, there seems to be some deep connection to because these non-solvable states is required for a universal gate set by braiding alone. So it seems that there should be some relation to states that can be prepared and whether they're universal for quantum computation or not. There is also a relation, if you allow measurement, it turns out there's some simpler gauge groups such as S3, which can perform universal quantum computation. But those are exactly the ones we cannot prepare with one round of measurement. So that there seems to be some connection there, which would be nice to work out in the future.
Cool. Any more questions? Oh yeah, I see one over there.
By brickwork states, you mean cluster state on the brickwork lattice, or? Well, the brickwork is exactly the honeycomb lattice. Is that right? Just so. And sorry, what was your question again? So by brickwork, you mean starting with a dense grid of 2D cluster state and then measure some stuff out? I mean, for the purpose of this, I'm just considering that the brickwork would be as easy to prepare because you just prepare Control Z on that graph. So Mhm. In 2D or 3D? 2D. I guess maybe you can chat afterward. I'm not quite.
Okay, we have time for maybe one more quick question. Anyone? I really wanted to ask something that this was all like an exact version, probability 1. What if you let it be like 1 minus epsilon?
Probability 1 of
reaching the state you want. What if it's just
so what are you allowed to not
what
be
do you
exact
just what if you just reach it with high probability after local unitary measurement and feed forward?
Yeah, that's a good question. I haven't thought
Does the
about
whole
that.
thing collapse or is it like robust?
That's a good question. I haven't thought about it.